Okay, this is me, my wife Jill, my son Henry, and big data. Some Star Trek fans in the house. So the unbearable lightness of data. Data to me is very light. It can be stored on heavy things, like a book, or something very light, like a thumb drive, or database appliances. But the data itself is very light. The oldest known data store from over 3000 BC was clay tablets, cuneiform written on clay tablets. And it's been estimated that a gigabyte of data on clay tablets would weigh about 400,000 pounds. So that's half of a Boeing 747 fully loaded. So this thumb drive can hold about 16 jetliners worth of clay tablet data on it. So data is very light. When you have big data, it's still very light. The value in data is you can see the unseen. You can see what's happened in the past. You can predict what's going to happen in the future. A CEO can know what's going on with their business, even though she doesn't have direct access, direct experience of what's happening. Or a marketer could predict and maybe influence the behavior of a consumer before it's happened. Data may be the most valuable thing in the world. I'll give you an example. The data, the binary information in the genome contains the instructions for creating a living being. Life exists on our planet because of data. And that's pretty valuable. And the structure of data can give it more value. So the genetic code in its structure can create life. We mapped the human genome about in 2003, the structure of the human genetic code. And that's available for download now off the internet freely. And I did it, it's a bunch of flat files and not a lot of value to me, but if you put that in a form, in a database that you can correlate with diseases and family histories, then medical researchers can predict, prevent, maybe cure diseases. So the structure of data can add value, a lot of value. So I love data, not the Star Trek data, but the information data. And I was thinking how far back this happened, and I think it all began when I was really into baseball. I was a baseball fan, and I liked the Atlanta Braves, and my favorite player was Hank Aaron, and he was in a race for the home run career record against Babe Ruth. And Hank Aaron inspired me because he would go in and day out in face of racism and hate, and he would get death threats and insults, and every day he would go out, do his job, hitting home runs, and he was my hero. I named my son Henry in part after Hank Aaron. So I was at the last game of the season when Hank had 713 home runs, and we were all yelling 714, 714, 714, and hit one more. And well, he didn't hit it that day, but early the next season he did hit 714 and 715, and he ended up with 755 home runs. But these numbers in baseball resonated with me. I love the batting averages and stolen bases and pitchers' ERAs and strikeouts. I love the numbers in baseball. And one day I was rummaging through a bookstore and found this most amazing thing. It was the Baseball Encyclopedia. And it was thousands of pages, and this is a later edition. It weighs about 8 pounds. You could use it in self-defense, I think. And it went away with the internet. But I saved up my allowance, bought it with my own money. It had the records of every major league player that ever played the game. And the very first entry in the book was my hero, Hank Aaron. So So I learned about sort order when I saw that. So this was my first database, really. It was partitioned by player with attributes about the player, but it had rows and columns. And in these rows, we had dimensional data. We had year and team, and we had fact data like hits and home runs and triples and stolen bases. And it had aggregate totals at the bottom. And then it had summary reports, like who were the top career hitters in hits in descending order, or what was the top 10 pitchers in ERA in a season in ascending order. All these different, you slice it by American League and National League, all of these reports, not unlike the reports that we do today for our Cognos clients. They're detail reports and summary reports. So I really loved these numbers, started working with them. And then the next year came around and baseball season started again, and this was out of date. So what I had was a one-time load, and what I needed was incremental updates. So I subscribed to a magazine called Baseball Weekly, and it gave me every week the latest statistics of the players playing the game and updated the career totals so you'd know who was chasing the records and how things were going, and follow those numbers. And I noticed that in the encyclopedia there was a number for a player back in the 19th century, total bases or something. And then the same total in the Baseball Weekly was different. And that just blew my mind. How could those numbers be different? And I wrote a letter to the editor. You know, what's going on with that? And I told my dad, who was a big magazine reader, and he talked about letters to the editor. You know, I wrote a letter to the editor of a magazine. And he said, "Oh yeah, which one?" And when I said Baseball Weekly, he rolled his eyes and wasn't very impressed. But it was a data quality problem. So I think the roots of my love of numbers came from baseball. After this, I went to college, studied computer science and mathematics, and started as a programmer analyst and for a manufacturing company. And so what we did at that time was we used COBOL programs to read files from the manufacturing system and produce these big stacks of green bar paper, and give people a stack of paper and give another person a big stack of paper. And they would look up things in these stacks, and they would look at the bottom line to get the totals. And it was like they had their own personal database that we were giving them. And this went for a while, and a new type of data structure came out called a relational database. We were able to use SQL commands against it, and we were able to make better reports, exception reports. We were able to respond to their requests for information. They could use their green screen monitors instead of the big stacks of paper. And this was an improvement on the way that we delivered information. And that worked for a while, but soon that was a burden on the source system. And the structure of the data in these databases were good for transactions and operational things, but not really good for reporting. So we had the idea, let's extract data out of that, put it into another system, and we called it the marketing information system. When we would aggregate the data along customer and product, the ways that made it easy for them to consume the data, and update that, and they would report off of it. And then we would make one for the sales area, for the sales force to do the same thing. And that worked well, unless they wanted to slice it a different way than we had already aggregated the data. And whenever we went to a different subject area, we'd design it differently. And when we got to human resources, it was a completely different thing we had to think about. And things weren't shared between sales and marketing. They're all specific to those reporting areas. So around the mid-1990s, Ralph Kimball appeared and had a new data structure called the dimensional model, the star schema. So we started using that, and that taught us to store the data at the lowest granularity that we had, and be able to roll it up in any way we wanted along these dimensions. And it not only was it fast, it performed well for the end users, but it was intuitive to them. They could write their own reports. They could drag and drop and write their own reports from it. So this data structure worked better than the one before. And then the internet happened. Well, the internet had been around a while, but one day it exploded like a supernova, and we had data coming out of smartphones, like waves of data coming out of our pockets and purses and wrists, and people knew things more about us than we knew about ourselves. And the kinds of data, text, tweets, blogs, audio, video, machine logs, the types of data coming out were different from the data that we'd been collecting from transactions. And the data was coming so fast that you couldn't really have time to store it. You could only sample it in real time to try to be able to make sense out of it. So this phenomenon, this new challenges of data, was given the term big data, and that stuck. But it's basically volume, variety, and velocity of data that exceeded our existing technologies. So to address these new challenges of data, new ideas came out. Now with the problem of volume, the idea was, don't put all of the data onto one machine and try to process it. Spread that across a number of servers. Distribute that data across a number of servers, and then process that in parallel. So Hadoop is a technology that is a leader in the ability to spread that data out and process it in parallel. For variety, the idea is don't make a schema and load your data into that schema. Load your data into a form that's much more flexible, and then apply the schema at runtime when you're using the data. And the NoSQL databases are the technology that have been successful in handling that kind of data. And for velocity, new technologies are being made to handle streaming data. And the basic concept there is you write an algorithm and you feed data through that algorithm and make decisions. Rather than running an algorithm across all your data, you run your data through the algorithm. So that's the concept with that. Now, Hadoop is basically two main parts for Hadoop. One is it has a distributed file system. So that means you can take the data, spread it across a number of nodes or servers, and it's fault tolerant because it has redundancy. It'll store the same data multiple times on different servers. And it's expandable, it's scalable. You can add nodes to it very easily and begin to spread more data across that. The second part of Hadoop is the parallel processing engine. And initially, that was called MapReduce, which was a Java-based program. And what MapReduce does is allow you to write a program that says, first, here's what you do with the data that you've got on your node. And then you take that, and here's how you combine it. And then once you've combined it, here's what you do with it. So you write these instructions on what to do in parallel and how to combine that. And that allows you to do parallel processing across all of these servers. There are a couple of challenges with this that have come about. One is the skills gap. It's hard to find people who can write good MapReduce programs. The second is that it's a batch process, so it can be slow. There's a lot of setup time to run the process, and then it runs, and then there's the finishing. So if you're just running a little bit of data, it still takes a long time just to get everything set up. Now, Hadoop has been hyped as the next big thing. Billions of dollars in Hadoop is going to be spent. Gartner just did a survey this year on Hadoop adoption rates. And what they found was that over 50% of organizations have no plans to use Hadoop whatsoever. About 18% plan to use it within the next 2 years, and 26% are using it today. Does that mean you shouldn't use Hadoop? Not at all. When you look at why, the two main reasons people aren't adopting Hadoop, 57% said that the skills gap was the problem. They don't have the skills to be able to install and program and make use of Hadoop. And 49% said they didn't know what value they were going to get out of it. So why would you invest in something you don't have the skills for and put in it and buy capital equipment for something that you don't know what kind of return you're going to get on that investment? So there's two ways to mitigate that. One is to leverage, don't just go out to the Apache website, download Hadoop, and give it to your people and say, okay, figure it out and make it happen. Use a distribution from a major vendor that gives a layer of ease of use across the top that makes it easy to provision nodes, easy to add programs to process, to schedule those, to get the output and work with it. Use a good distribution to do that. And the second way to mitigate those problems are to leverage the cloud. So instead of investing in a bunch of infrastructure to be able to try this out, use the cloud to provision nodes of Hadoop and start small. And once you find that area, that use case that adds value, then you can scale that up as big as you need it to be. And the resources and a cloud vendor can help you with the skills gap and also with the capital outlay that you would have to have. NoSQL databases were designed for variety, but there's a couple of aspects about them. One is that they're distributed. NoSQL databases can be spread across multiple servers, and that was something that was hard to do with relational databases. But NoSQL was designed to do that. Some of your data could be in New York, some in London, some in Hong Kong. The other is that the data is either very unstructured or lightly structured so that it can handle a large variety of data. The one exception to these characteristics is the graph database. And that's not like pie graphs and line graphs. It's a mathematical idea of nodes and their relationships. So think about Facebook users and their friends and their network of friends, or LinkedIn and their connections, and being able to query this and analyze and find who are the hubs and who are the influencers and that sort of thing. So graph databases were not designed for distributed data necessarily, but they're lumped into this category because they're not traditional databases. And they're called NoSQL, but NoSQL doesn't mean NoSQL. Because of the prevalence of SQL skills, almost all of these can be queried using SQL, either with the tools or third parties have provided the tools to do that. So you might think of it as not only SQL, but it's basically not relational is the idea of that. So leveraging the cloud gives you the opportunity to either provision servers in the cloud, infrastructure. You can add servers, specify the amount of RAM disk space that you need, how many you need. You can add to that, subtract from it. That's the infrastructure of a service. Platform as a service is a platform for developers to work with source code control, and they can build and deploy and test cloud applications on the cloud. And software as a service is using software immediately. You don't have to install it on your servers and configure it and worry about upgrades and so forth. You can begin to use it immediately. In big data, software as a service means things like reporting software or statistical analysis software or MapReduce kinds of processing. So returning back to one other thing about this, the mindset of managers is that the cloud is something that is going to replace IT and save money. And that's not the way it works with big data. With big data, the cloud makes you more agile. It allows you to use kind of an options approach. Spend a little money now, and then as you can prove its value, spend more money. So that's the main way to use the cloud as in the big data environment. So we talked earlier about the human genome, and a new article in the Journal of Nature just came out where that original human genome baseline structure that came out in 2003 is a little flawed. The way people have their DNA sequenced is they compare their genetic structure against that baseline model. And what they found out is and about 250,000 people have had that done. What they found out is that it doesn't quite fit 5% of the time, and that some of those areas that don't fit have been associated with autism and what makes us different from apes. And what this company has found is a new way to model the human genome so that you can get a good fit. And what the secret is a data structure. They're using a graph data structure like the LinkedIn and the Facebook to model the human genetic code so that you can get a good fit instead of a more flatter structure. So data structure does add value. So in summary, data is very valuable. It may be the most valuable thing in the world. Data structure adds value. As we've had challenges with working with data, new data structures have been invented to overcome those challenges. And those challenges of heavy volume and broad variety and fast velocity have been addressed using the technologies of Hadoop and NoSQL, and you can make this easier to implement by leveraging the cloud. So, in conclusion, I love data, and I've spent my life working with new forms of data, new ways of working with data, and big data is just a name. It really means looking for new ways to source data and structure it in a way that you can learn more about what you can't see. So you have data today in your systems or available to you right now that can transform the way you do business. And I'm going to close with a quote from my hero, Hank Aaron. He said, "It took me 17 years to get 3,000 hits in baseball. I did it in one afternoon on the golf course." No, that's the wrong quote. Sorry. He said, "My motto was to keep swinging. Whenever I was in a slump or feeling badly or having trouble off the field, all I needed to do was just keep swinging." So use this conference, go out today and start using Hadoop and NoSQL and the cloud and discover the possibilities. If that doesn't work, try something else. Keep swinging.